we already know that when we differentiate log x, what we end up with is 1 over x. We also know that if we've got y equals a log of a function of x, and we differentiate it, then what we end up with is the derivative of that function over the function of x. Now, the point about integrating is if we can recognise something that's a differential, then we can simply reverse the process. So what we're going to be looking for, or looking at in this case, is functions that look like this, that require integration, so we can go back from there to there. So let's see if we can just write that little bit down again, and then have a look at some examples. So we know that if y is the log of a function of x, then dy by dx is the derivative of that function divided by the function. So therefore, if we can recognise that form and we want to integrate it, then we can claim straight away that this is the log of the function of x, plus, of course, a constant of integration, because there are no limits here. So we're going to be looking for this. We're going to be looking at what we've been given to integrate, and can we spot a derivative over the function, or something approaching a derivative. So now we've got the result, let's look at some examples. So we take the integral of tan x dx. Now it doesn't look much like one of the examples we've just been talking about, but we know that we can redefine tan x as sin x over cos x. And now when we look, the derivative of cos is minus sine. So the numerator is very nearly the derivative of the denominator. So let's make it so. Let's put in minus sine x. Now, having put in the minus sign, we've achieved what we want. The numerator is the derivative of the denominator. The top is the derivative of the bottom. But we need to put in that balancing minus sign so that we can retain the equality of these two expressions. Having done that, we can now write this down, minus, and it's that minus sign, the log of cos x, plus a constant of integration c. We're subtracting a log, which means we're dividing by what's within the log function. So we're dividing by cos. And what we do know is if we're dividing by cos, then that's 1 over cos, and that's sec. So this is log of sec x plus c. Now, let's go on again and have a look at another example. Integral of x over 1 plus x squared dx. Look at the bottom and differentiate it. Its derivative is 2x. We've only got x on top, but that's no problem. Let's make it 2x on top by multiplying by 2. If we've multiplied by 2, we've got to divide by 2, and that means we want a half of that result there. So now this is balanced out, and it's the same as that. What we've got on the top now is very definitely the derivative of what's on the bottom. So again, we can have a half the log of 1 plus x squared plus c. We can even have this with what look like very complicated functions. So let's have a look at 1 over x times the natural log of x. Doesn't look like what we've got, does it? But let's remember that the derivative of log x is 1 over x. So if I write this a little bit differently, 1 over x divided by log x dx, then we can see that what's on top is indeed the derivative of what's on the bottom. And so again, this is the log of x plus a constant of integration, c. So even in something like that, we can find what it is we're actually looking for. Let's take one more example, a little bit contrived, but it does show you how you need to work and look to see if what you've got on the numerator is in fact the derivative of the denominator. So let's have a look at this. Looks quite fearsome as it's written, but let's just think about what we would get if we differentiated x sine x. And I'll just do that over here. Let's say y equals x sine x. Now this is a product. It's a u times by a v. So we know that if y equals uv, when we do the differentiation, dy by dx is u dv by dx plus v du by dx. So in this case, u is x and v is sine x. So that's x cos x plus v, which is sine x, times by du by dx. But u was x, so du by dx is just 1. And so if we look, what we can see here is that the numerator is x cos x sine x, which is the derivative of the denominator, x sine x. And so again, complicated though it looks, we've been able to spot that the numerator is again the derivative of the denominator. And so we can say straight away that the result of this integral is the log of the denominator, x sine x. Sometimes you have to look very closely, and let's just remember, if we just look back at this one, that sometimes you might have to balance the function in order to be able to make it look like you want it to look. But quite often it's fairly clear that that's what you have to do. So do remember, this is a very typical standard form of integration, a very important one, and one that occurs a great deal when looking at differential equations.